As the cathode ray oscilloscope has become a tool of ever-increasing necessity in research and industry, there is a greater demand for instruments of increased accuracy and improved performance. Tektronix Incorporated was organized with the primary purpose of furthering the development and improvement of the oscilloscope, not only as a qualitative device, but rather as an accurate tool, capable of precise quantitative measurements of time and amplitude. To build instruments capable of being calibrated to a high degree of accuracy, it has been necessary to design amplifiers and sweep generators of great stability and linearity. One of the limiting factors in the design of such instruments has been the cathode ray tube itself. As sweep circuits and wideband amplifiers became more highly developed, it becomes apparent that further improvement in overall accuracy and performance of the oscilloscope is dependent on improved cathode ray tubes. As tubes of higher deflection sensitivity were developed, faster, more linear sweeps and vertical amplifiers of greater bandwidth became possible. In addition to high deflection sensitivity, good focus, high brightness, and very precise image geometry are essential. Several years ago, we at Tektronix decided the best method of obtaining the improved tubes necessary for advanced types of instruments was to manufacture our own. The purpose of this film is to show some of the methods and processes used in the development and manufacture of Tektronix instrument-grade cathode ray tubes. No matter how great the pains taken in the assembly and manufacturing of a tube, the finished product will be no better than the fundamental design engineered into it. Therefore, the first and most important problem was to get a satisfactory design for the tube itself. Several years' time was spent, and many experimental models were made before we reached the conclusion that we had a tube that was enough superior to those commercially available to warrant its manufacture. In the design of some electronic equipment, it is possible to cut and try until the optimum values are obtained. However, since all of the parts are in a high vacuum, it is impossible to reach in and move a part or make an adjustment in the design of the tube. Therefore, most of the design work must be done on paper. A tool that has been a big help in the design of the electron gun has been a computing board made up of thousands of precision resistors. This board permits the operator to set up voltages at various points on the board, corresponding to the potentials on the electron gun. It is then possible to measure the potential at any point with a vacuum tube voltmeter. A plot of these voltages will give us a chart of the electrostatic voltages within the gun itself. In order to verify the calculated gun design as easily as possible, a demount tube was constructed in which various gun designs could be tried. This permits a more rapid check than if each gun had to be sealed into a glass envelope and then evacuated. This demountable construction permits changes to be made in the placement of the gun parts without destroying the tube. It is only necessary to open the tube, move or change the part, close it, and re-evacuate it to see if an improvement has been made. A cathode ray tube consists of many small parts, which must be made with a high degree of precision. Since the performance of the tube depends upon the accuracy of the shape and placement of these parts, it has been necessary to make the dies and jigs and to punch or machine these parts in our own plant. This machine forms stainless steel wire into accurately shaped spacers, which will be used to mount the gun parts. Certain of the gun parts, such as the deflection plates, must be formed to very accurately controlled shapes. At first, an attempt was made to form these parts in an automatic bending jig or die. However, it was soon found that the amount of springback varied from one batch of metal to another, and therefore it was better to form these by hand and to check each individual part. These parts must be accurate and parallel, and are held to a tolerance of better than 1/1000th of an inch. The deflection plates are placed in a jig, and the mounting leads or spacing tabs are spot welded on. These spot welders are of the stored energy type. A capacitor bank is discharged through a thyrotron tube into the primary of the welding transformer. The current and the time of the weld can be accurately controlled. An air cylinder supplies a constant pressure on the welding electrodes. Here, the spacing wires are being welded to the anode assembly. The wires are trimmed and shaped in this machine. Most of the gun parts are made of highly polished stainless steel. These look like perfect parts. However, there are still microscopic imperfections on the surfaces and edges of the metal. So each part is electro-polished by passing a high current through it in a special electrolytic solution until all surface irregularities are polished away. As the parts come out of this bath, their surface is much smoother than if they had been polished on a buffing wheel. The parts are again inspected and are then fired in a hydrogen atmosphere furnace to remove any oil or other impurities trapped in the pores of the metal, as well as removing all surface oxides. A suitable source of high purity hydrogen in sizable quantities is needed to operate this furnace, as well as to supply other operations in the manufacturing of the tubes. To supply this need, we have installed a generator which cracks ammonia gas, NH3, into hydrogen and nitrogen under high temperature with the aid of a catalyst. After suitable processing in the hydrogen furnace, the tube parts are chemically clean and free of all surface oxides and are ready for assembly into a complete electron gun. After this stage, the gun parts are never touched by the fingers of the operators. Extreme cleanliness is a necessity. The complete plant is thoroughly air-conditioned. The heart of the electron gun is the oxide-coated cathode. The base metals upon which the cathode is coated are preconditioned in an alkaline solution, washed and dried. The cathode assemblies are then placed behind the openings in a metal mask. The spray gun is moved by means of a lead screw to ensure a uniform coating. The suspension of alkaline earth carbonates and the special binder are kept mixed with a small electric motor mounted right on the spray gun. The thickness of this coating is very important. Many passes of the spray gun must be used to build up a uniform layer. The coated cathode is checked under a microscope to make sure that the coating is uniform and of proper thickness. They are stored in airtight containers until used. The prepared cathodes are placed within the grid assembly. A retaining ring positions them in place. In order to maintain the proper grid cutoff voltage, it is necessary to hold the grid to cathode spacing to a tolerance of better than 5/10,000ths of an inch. Each assembly is measured and inspected with the aid of a microscope. The retaining ring is welded to the grid assembly, ensuring permanent alignment. Several methods of assembly of an electron gun are possible. One method which has found some use is to cement the part to metal or ceramic rods with a ceramic-type cement. Another method is to align the parts with mica washers and use metal rods to support the washers to maintain the alignment. These methods were tried, but were soon discarded as they tended to be too fragile, and it was difficult to hold the tight tolerances necessary in a precision cathode ray tube. A better method is to fuse all of the gun parts into glass rods. This assures a permanent, accurate alignment of the gun. This is the method which we have adopted, but it is not without its problems. One of the problems was that the Pyrex glass necessary to maintain dimensional stability is such a perfect insulator that charges tend to build up on the rods during operation of the tube, and sometimes cause distortion of the trace. We overcame this problem by lightly coating the Pyrex glass rods with a preparation containing lead oxide, which fuses into the glass as it is heated and forms a microscopic layer of lead glass on the surface of the rods. Tight tolerance is of prime importance in the assembly of the electron gun. It was necessary to design and build precision jigs which would accurately align the gun parts into a very rigid assembly. The vertical plates are placed in position. These plates must be parallel within a fraction of a degree. The spacing between elements must be held to an accuracy of better than 1/1000th of an inch. Accurately ground spacers are placed between the grid, the focusing electrode, and the anodes in order to maintain their spacing. The horizontal plates are clamped into position. In a rigid assembly such as this, there can be no variables introduced by the operator. A prepared glass rod is placed in position. The alignment of the assembly is checked. The gas flames quickly bring the glass rod to white heat. Now the gun parts are forced into the soft glass and permitted to cool. Another rod is placed in position. The gun is rotated 90 degrees. It is indexed in position, and the operation is repeated for each of the other rods. Here we have a completely assembled electron gun, consisting of a grid assembly containing the cathode, a first anode, a focusing electrode, a second anode, the vertical plates, an interplate shield, and the horizontal plates, all firmly fused into 4 glass rods. The first step in the manufacturing of a precision cathode ray tube is now complete. Tabs are fused into the ends of the glass rods to permit the gun assembly to be mounted onto the stem. The complete gun assembly is again placed in a special jig. The glass stem is carefully positioned in the jig. Permanent alignment of the gun is assured by spot welding the gun assembly to the wires in the stem. The coiled heater is inspected under a microscope to be sure that there are no breaks in its insulated coating. The heater is positioned within the cathode sleeve. A steady hand and a sharp eye are needed for this operation. Tweezers are used to connect the ends of the heater wire to the connecting tabs. The heater wire is spot welded in place with tweezer-type electrodes. The connecting leads to the other electrodes are welded to the leads in the glass stem. The getter assemblies are welded to the gun. Tabs are also welded to the gun assembly, which will make contact with a dag on the inside of the tube and will also position the gun within the tube neck. The finished electron gun is now placed in the chuck of a glass-blowing lathe. A length of glass tubing is placed in the chuck in the other end of the lathe. A glass-blowing lathe differs from a regular machine lathe inasmuch as both the headstock and the tailstock are driven and rotate at exactly the same speed. A broad flame is applied to preheat the glass. A fine, hot flame now softens the glass. The two parts are now brought together and the glass is fused. A carbon tool is used to smooth up a high spot. An extra flame completes the fusing of the parts. The broad flame is again applied to anneal the glass and to relieve stress. The sealing is now complete. The glass is scribed with a carbide tip tool in order that it may be cut off at the proper length. The completed gun assemblies are stored in dust-proof plastic cases awaiting further operations. The deflection plate terminals are placed in position. A jig is used to ensure accurate position of these terminals. In order to maintain this alignment after the assembly is removed from the jig, a spacing wire is spot welded to the terminals. This wire will remain in place until the tube is completed. A final inspection completes the work on the electron gun. As the gun is being assembled in another department, the glass envelope is being prepared. The glass is accurately scribed and is cut off on the scribed line by means of a hot wire. The glass envelope is carefully washed. Extreme cleanliness is a necessity. Many of the rejects of the finished tube can be traced to lack of attention at this stage. The glass must be surgically cleaned. A trace of dirt or heavy metal might cause poisoning of the screen. It is lightly etched with a chromic acid solution to actually remove a thin layer of glass along with any dirt or foreign matter. It is rinsed and dried. To ensure a uniform post-acceleration field, Tektronix has pioneered the use of a helical resistive spiral applied to the inside of the tube envelope. This resistive material is applied by means of a ruling pen to the inner surface. The composition of this material, or ink, must be accurately controlled to get a uniform resistance. It must be of such a nature that it will bind itself firmly to the glass and not flake off or become dislodged. It was found that it must be mixed at least 12 hours before its application, and it becomes unstable and worthless if stored for more than about 20 hours. This ink consists of finely milled carbon particles suspended in a special binder. Ethyl silicate is added to slightly dissolve or etch the glass as it is applied, thereby bonding itself firmly to the envelope wall. DAG is applied to the ends of the tube to make contact between the resistive spiral and the post-acceleration terminal. The envelope is baked at high temperature to dry and set the resistive material and the DAG. The screen material, or phosphor, is carefully mixed and weighed out. Both the composition of the material and the amount used are very critical. A small change here can make a great change in the light output from the screen. The inner surface of the faceplate is again cleaned and lightly etched with a solution of hydrofluoric acid. The first step in the settling of the screen is to pour a measured amount of distilled or deionized water into the envelope. This acts as a cushion through which the screen material will settle by gravity. The temperature of the solution and of the surrounding air must be carefully controlled to prevent convection currents within the solution, which might cause uneven settling of the screen material. The final settling is done on special racks, which may be tipped in order to pour off the excess liquid without disturbing the phosphor material, which is settled on the tube face. This rack must move very gently, as the screen is very fragile at this point. An air cylinder is used to tip the table. The tube envelope is now dried in an oven. This firmly bonds the screen material to the tube face plate. The light output of a high voltage cathode ray tube is improved, and the flare or halation is reduced if the screen is metallized. It is not practical to deposit the metal directly on the phosphor. It would give a rough, non-continuous coating. Therefore, a thin lacquer film is first deposited on the phosphor. This is done by first placing a solution of water and acetone in the tube. A few drops of the lacquer are then floated on this solution. This spreads out to the surface of the liquid and forms a uniform film. After this lacquer film is hardened, the water is carefully poured out from under the film, leaving it in direct contact with the screen material. The screen is dried on these tables by jets of warm air directed onto the faceplate. In order to deposit the metallizing layer on top of the lacquer film, a small pellet of pure aluminum is placed on this tungsten heater. The tube envelope is inverted over the heater, and a protective plastic shield is placed over the envelope. After the tube is evacuated, the temperature of the heater is slowly increased until the aluminum is vaporized. The vapor immediately condenses onto the cool face of the tube. We have deposited a uniform aluminum film of a thickness of only a few microns. The tube envelope is given a final baking now at high temperature. This operation completely dries out all the remaining moisture, as well as burning out the lacquer separating the metallized film and the screen material. The final step in the mechanical assembly of the cathode ray tube is the sealing operation. The prepared envelope is accurately positioned on the chuck of a glass-blowing lathe. The electron gun assembly is positioned in the other chuck of the machine. A broad flame preheats the glass. The fine hot flames quickly softens the glass, and the parts are brought together. The sealing is now complete. The broad flame is used again to anneal the glass and relieve stress. The tube is now ready for the final, but one of the most important processes. It is sealed to the vacuum pumps. As the tube is being exhausted, the metal parts are heated with radio frequency energy from an induction heater. This helps to drive out gas trapped within the pores of the metal. An oven is lowered over the tube. This will heat the complete tube to a temperature just under the softening point of the glass. The temperature must be very accurately controlled. Only a few more degrees and the bulb would collapse. If a relay should happen to stick, we get a tube that looks like this. Each of the pump stations consists of an exhaust manifold, a water-cooled charcoal trap, an oil diffusion pump, backed up by a mechanical pump. Careful attention and extended pumping time permit an ultimate vacuum close to 1 times 10 to the minus 7th millimeters of mercury to be reached, even before the getter is fired. This high vacuum does much to extend the expected tube life. Almost all early failures of cathode ray tubes are due to gas molecules in the tube forming positive ions when they are struck by the electron beam, and these ions soon destroy the cathode material. After the pumping is almost complete, the getters are partially fired by means of an auxiliary induction coil. This assists in clearing up any remaining gases. The pumping is now complete, and the tube is ready to be sealed off. A flame is applied to the glass seal. The glass is softened, and internal vacuum pulls the walls of the tubing together. The seal is completed. The excess glass is removed, and the seal is smoothed over. A broad flame anneals the glass and relieves any stress. The base connection leads are cleaned and are formed to shape. The base is filled with cement and fitted onto the tube. Excess wire is trimmed off. The base area of the neck is baked with radiant heat to set the cement. The leads are soldered to the base pins. Any soldering flux remaining on the pins is brushed off. The getter tabs are heated with an induction heater to vaporize the getter material. To remove any trace of magnetism remaining in the stainless steel tube parts, the complete gun assembly is demagnetized by passing it through an AC field. The tube is now complete. However, it still would not work. First, the cathode must be activated. This is done by applying voltage to the gun elements, wired as a diode, and flashing the heater at accelerated voltage. The tube is now ready to operate, but first it must be aged to permit its characteristics to become stable. This is done in special aging racks. Full operating voltages are applied to all tube elements. The design and manufacturing of a precision cathode ray tube is not an easy task. However, by strict attention to small detail, by rigid control of all materials used, and careful inspection throughout the complete process, a tube of superior performance can be produced. If one ingredient is more important than the rest, that ingredient is the worker's pride in good workmanship. If one operation in the building of a superior tube is more important than the rest, that operation must be the final testing. It is only after checking for focus, spot size, cathode current, beam current, light output, as well as linearity and alignment of the trace, that we can tell if all of the work which has gone before has been well done. The planning and care that have gone into the manufacturing of these tubes determines their fate at this point. Only a tube which has satisfactorily passed all tests is eligible to carry the Tektronix emblem. This emblem is the token of our pride in a good product. Our continuing creed is that of serving Tektronix customers with products and policies that are unexcelled in the electronics industry and limited only by the current state of the art.